In this lecture, I will introduce you to logistic regression, which is one of the most widely used applications of GLMs, and so much so that so many people end up using the term logistic regression and GLM interchangeably. Logistic regression is carried out in situations when our response variable y is categorical. So when we have binary categorical variables like yes or no, success or failure, 0 and 1, and the predictors are numerical. The null hypothesis is that the probability value of the nominal variable or the response variable is not associated with the value of the measurement variable. And essentially, this is how this is the formula that we use for probability of y happening. That is the probability of y being a success or 1, and this is the default mode of logistic regression. So py, probability of y equaling 1 or yes or success, is computed as 1 raised to power 1 plus e raised to power and beta alpha plus beta 1x, and this is what you find in the equation of linear regression as well, and we find the same thing over here in logistic regression. I will not go into the mathematics of all this because the upshot is that you only need to remember that if you want to compute the probability of y happening, and assuming your y is a categorical variable, this is the formula you are going to use. Another important aspect of logistic regression is logit, and essentially it stems from the fact that linear regression needs a linear relationship between x and y, but this condition is violated in case of when y is categorical, and that is why we end up doing logistic regression in the first place. And logarithmic transformation is used for expressing the non-linear relation that now ensues in a linear way, and this is known as a logit. And essentially based on this is how this particular formula comes about. Essentially we end up taking the log of y for our linear regression equation, and once we solve it we end up with this. Another thing that we hear in the context of logistic regression, and this is something you may have to calculate for your data, are odds, and odds are computed by taking the exponential of beta, and essentially this is the probability of success. So if you were to obtain the values of these parameters and so on, you could easily get the probability of success, and you can substitute that like so: probability of success divided by probability of failure, or take the exponential, and that tells us that essentially what are our chances of succeeding. And associated with that is something known as odds ratio, which is the odds of success divided by odds of failure. So we are x number of times likely to succeed or x number of times likely to fail, depending on how you interpret that computation. So these are the other two things that you may obtain from your logistic regression once you have the probability of succeeding in the first place. And the assumptions of logistic regression are that there is a linear relationship between x and the logit of y. There is independence of errors, and errors don't have to be normally distributed, and that is why we end up performing GLMs in the first place. And these are quintessentially the type of data we end up performing logistic regression on. Well, we do associate logistic regression on with categorical response variables, and that is true, but later on in this lecture I'm going to show you another case when we may not have strictly categorical variables. So this is the sinusoidal S-shaped distribution that you need to bear in mind, and when you have this sinusoidal kind of distribution with your data, then it's a good time to consider logistic regression.